Welcome back, folks. So let's continue with this very interesting case. So to revisit the problem, what we're doing is that we have this geometry for the same variables, and we want to minimize drag using different methods. So far we study derivative-free, gradient-based method, and design-based exploration. So we studied the major groups. So I hope now you have a better idea how things work in Dakota, but general optimization. But everything that we did was single objective. In this video, we're going to do multi-objective optimization. That is, we want to minimize drag and maximize lift and whatever. Okay, you can have it in many combinations. So, but this is our goal. And when we do this, things change a little bit. So we cannot use gradient-based method, or better to rephrase that, yes, you can use, but it's not the most efficient way. You need to use specific methods that are formulated for this kind of multi-objective optimization problems. So how it looks like a multi-objective optimization problem, just let me show you, that you're going to have the design space and the output space. So here we're looking at the output space, the quantitative interest 1 and 2. And basically what you are doing is just sampling your design space, getting the best solutions, and then you are going to construct what is called a Pareto front. Okay, so this Pareto represents the best overall solution. That is, you cannot get anything better than this point. So you can start something from somewhere like this, and it will evolve until you get until the Pareto. So here we can see the animation of a case, and we can see what is happening. So you have the overall population, which are these blue dots, and then you're going to have population by population, population 1, 2, 3, following some certain rules that usually are genetic algorithm, but there are different techniques. Okay, I like to use genetic algorithm, but by no means that is the only method. But look at how things are evolving very slowly, and then the method is discarding the solutions that are dominated. Okay, so the green dots represent the non-dominated solution, the Pareto front. So here we see better how things evolve. And this is the idea. As you can see, it is an iterative method, a brute force method, requires many functions evaluation. However, positive note is that it has a high level of parallelization, because each of these solutions that you're computing here, they are not dependent. You can launch many tasks at the same time. So we come back to this topic that I have mentioned, that it's very important to know your computational resources and choose a method that has a high level of parallelization, because you can get faster outcomes. So this is the general idea, and now let me show you a very specific problem so you can get a better idea of what is happening. It's a super easy problem. So imagine that we have two functions, these quadratic functions. So as you minimize this one, these independent functions, you know that the minimum is 0 and the minimum is 2. Okay, but that is just one situation. However, when I have that is the situation, independent function, single objective. But when we go multi-objective, that those functions are dependent, you don't have a single solution. And we can see here, we have these two curves. So in the previous case, that was single objectives, independent functions, you have a minimum here and a minimum here. But now things are linked together, are dependent. So in this case, when you minimize the red function, you're going to have a value, a corresponding value in the blue function. And this value might or might not be the minimum or the optimal value for that function. So in this case, we're minimizing both of them. So see, when you minimize this one globally, you get the global minimum, you get this value that is not a minimum, but is a better value than whatever you have here. So start to see that you start to construct your solution. You start to do iterations, you get a minimum here, the value corresponding to this one. If you move in this direction, it's not an optimal solution, so you move in this direction. So see that now you start to move in this direction, and all these solutions here are optimal solutions. You are minimizing the functions. It's not a global minimum, but you are minimizing. And then you keep moving, and you reach this point where now you reach the global minimum as the blue function, and then you have the red one that is not a minimum, but it has a better solution than any other solution in this side here. So now you can see that all your optimal solutions are concentrated somewhere here. So as you can see, you don't have one single solution. You have multiple solutions. And at this point, it's up to you to pick up one, okay? It is very subjective, and you need to know very well your problem. And usually when you're doing this one, since will become multidisciplinary, okay? You will need to link this problem with another discipline. So for instance, talking about aerodynamics. So you're doing aerodynamics, then you need to link this to structure computations, no, structural mechanics, or maybe with performance or whatever, to get that better solution. So when we look now in here, we have the design space, and this is the space of the quantity of interest. So look that all these solutions here represent the possible cases, not a single one. So you have this one, and this one will be the global for each function, but then in between you have many solutions. Something interesting that some people might say, but your global optimal will be the intersection of these two. So in this case, they do intersect. We're using two functions, but remember that can be multivariate. You can have 100 So that situation is not going to happen. But also, your global optimal is not represented by the intersection. Okay, it can be any of the solution. It is up to you to pick up one. And this is your Pareto. This is what you construct at the end of the day. So design variable space and quantity of interest space. You put everything together, and you have this Pareto. As you can see, okay, each of these cases that will be a better solution, or in reference with the non-dominating solution, what we discarded in this part here. So it's up to you to pick up one. So in this case, we have no quantity. The quantity of interest, the objective functions are competitive, meaning that if I increase one, the other increase. You can have it also opposing. You increase one, the other decrease, and so on. Also, this is not the only shape of this Pareto. It can be like this, can be like this, like the other direction, and so on, and it can be discontinuous. So this Pareto can come in many flavors. So this is it now. What happens in multi-objective optimization? And to illustrate with another problem, this one it was trivial a little bit. It was a super simplification, but it's an interesting case. So it's a little bit more practical. So now imagine that you want to optimize this con here, and what you want to do is minimize S, which is this variable, and minimize T, which is this variable. So it's the summation of B and S. B, it is the base area. S is the lateral surface. So basically we want to minimize these two, and also we have a nonlinear constraint. I want to guarantee that the volume is always more than 200. So when we talk about nonlinear constraint, is this one something that is derived from your design variables? It's not directly computed, okay? So you need to compute that. These are your linear constraint, okay? The limits of the design variables. So these are very easy to implement. These are unique to compute it, to give it to the method, to the iterator, to the library, whatever you are using. So this is the problem. And what is interesting that if we look at the previous case, now that we have the quadratic function, is you look at the streams. In this case, you can get these two solutions, which are optimal solutions. So here, this is the global minimum of S and the global minimum of T, and you get these two solutions. And to get these two solutions, you can use a gradient-based method. So you are in your design space, whatever it is your design space, and you start from an initial position, and you can converge to this or something else. But as you can see, if you use derivative free, it's quite difficult to get all those feasible solutions, because you need to run many iterations. So here's where you start to see these genetic algorithms become very efficient. But what is also interesting that you get these two solutions, but in between you have many more solutions that are a good solution as well. Not necessarily these two or just one, it will be the best solution. So there are many solutions in between that you need to compute, and those solutions in between that we compute using, in this case, the Morgan method, multi-objective genetic algorithm, it will be given by this Pareto. So this Pareto represents all those solutions. And look at here, there's this green dot here represent this solution and this solution that was obtained using a gradient-based method. Okay, so I started from several locations until I arrive here. So it's quite interesting because you can start from somewhere here and it's not going to arrive to a point here. It's going to arrive or here. And to get these points, maybe you need to get closer. It's very tricky. You will get the idea, and I invite you to try to do that. So I got this too up just as a reference using gradients, and then the Pareto constructing, using different actions, different iterations, and so on. So it will change according to those hyperparameters that previously we talking data free about those, and it's tricky to it is tricky to calibrate those, but usually default values will give you something acceptable. Okay, so this is the idea, and this is what we have. Reminder, this is time consuming. You will do a lot of iterations. So we're going to work in this case using this very interesting geometry. So let's go back here and let's do multi-objective optimization. Okay, so enough of talking, and now let's do practical stuff. So in your folder, in your directory there, in the case, you're going to find here, we have done so far all this stuff, and now we're going to do this. So this is multi-objective optimization, and this is multi-objective single objective. Then I'm going to explain what do I mean by that. So as you enter in this one, you have the standard case structure. So I already have it, I open it here. So you have your Dakota case in, you define everything in the usual way, and then you shall select the method. So in this case, I'm going to use MOGA for multi-objective. And then you have all these parameters. So in this case, we have a maximum number of 2000 function evaluation. This is the random number for the initial population, the size of your initial population that then is going to change according to some rules that are given by all these parameters that and using default values. So look at that, you have offsprings, parents, crossover rate, mutation rate, and so on. So many parameters that you can calibrate just to change the convergence. And then yeah, you have your initial population, and that's all. So as you see, I commented everything. So by the way, I think I haven't mentioned that the comments in the dictionaries in Dakota is using the numeral hashtag or whatever you call it, pound symbol, I don't know. So everything is commented except for the method, maximum number of function evaluations, and the set and the population size. This one I like to put it always, it will print my populations. You can see the evolution, but in theory everything is optional. So as usual, I repeat here that I will go to documentation, so please get familiar with the documentation, and I look MOGA, and here you will have that basically pretty much everything is optional. So if you want, you don't give anything, put MOGA, use default values, and that's all. Here exactly the same, you define everything. Remember, here you can explode the parallelization. So in my case, I will use 16 cores, but if I had 100 or 1,000, you can put there that and it will work. Okay, no problem on that. Everything here, and now we stop here. So remember, multi-objective, all the previous cases we were doing single objective, one objective function, except if I were recalling design space exploration. In some cases I put there 3 or 4, but there were not optimizing. It means that you can get 4 responses from that experiment. So we're not doing any optimization there, remember. So here's multi-objective. So we want 2 objective functions. We don't compute gradients and Hessians, so this method doesn't use that. Then later we're going to redo this exact case, and I'm going to show you nonlinear constraint, how to introduce. You already have it there, but I will show you the difference and why do I want to introduce. So to stress importance, know your problem, know what you're doing, formulate your problem. And here what we want to do, sense, minimize the first one, maximize the second one. In this case, my first will be drag, the second will be lift. So this is how I compute in those variables. It can be in any order, by the way. So if I go to the simulator script, pretty much everything is the same. The only thing that will change is here when I compute the post-processing. So here's where I choose the order of those variables. So I have here where I save that result files is here. So remember that these results here, when I move it to results.out, this is what Dakota will take. So for this file, see that I'm computing the mean values of, this is the drag and the lift. So basically I just put in that data here, and then I will move files, and those files I will move it here. So I hope you are not confused by this operation that I'm doing here. So here I just computing using AWK, computing the average of drag and leave. That information is saved in this file results. So here I resolve. So you're going to have those two values, and then this operation here results CP results to $2. Remember, $2 will point to this variable results.out. So basically here what I'm doing is just copying this information results into results txt into results out. Yeah, I know I can name it directly here, but just to avoid problems, I like to have this one kind of a backup file to check if everything is okay, and then I do the name substitution. So that is what is happening there. So everything is ready to go. I'm not going to check the files and everything because I have everything there. But remember, before running, always check that you have all the files, everything is set up in the proper way, so you don't waste time or your simulation doesn't crash because you are missing something. So let's run this case, and I will go here, then go Dakota clean up. Okay, to clean everything. Another reminder, so sometimes might happen that you don't have execution permission to this file, so you need to give execution permission 755. So I always like to enforce that. So as you go here, see that you have execution permission. So be careful about that. And at this point, I can run. I would run and also save the log file. So usually here in the header, I put it, you know, how I like to run to save everything. And this is going to run with 16 core. This computer is going to become very noisy. The fan is going to kick in, and yeah, it's going to do about, I don't know, I think I will recall like 2000 iterations. I don't recall well, but in any case, this will take a while. So at this point, I will stay quiet and let it run. Okay, here the fans are kicking in. So let's see if you can hear the fans. Okay, I hope you hear that. So well, let's wait for the final solution. Okay, so I'm back. We have a solution. Okay, the fans of my computer is still very loud. Oh, you're not hearing that, but any case, so that was one. As you can see, a lot of function evaluation, but it is the computer doing the work. Okay, we're just sitting here watching. So all these iterations, and yeah, I just left there the processor. So as you saw, everything was running in parallel. All the 16 cores are using, or I use using 16, but I can use up to 24. And now let's take a look what happened here. So we run the multi-objective. It ran a boatload of function evaluation. So as you see, you have all these folders, and I want to stress again, be careful with the space, that you can easily run out of space if you're running large cases. But what interesting is in these files, okay? So remember, you have the restart file. So as you saw, nothing crashed. Okay, so it's fault tolerant, but in the case that something crashed or whatever reason you stop it, you have the restart file. We already saw also how to explore this restart file. And then we have here the population. So the populations here, you see how it is evolving. So you start initial population. Later I'm going to plot this, and then you will see that since it's going to evolve, move towards the direction of improvement. Table out, you will have all the functions evaluation, and then in final data discard, you have all the discarded point, and here you have your final solution. So let me open that, because in SOG it was a single point. Now here see that you have a multiple points. So now this will be your Pareto. So what you see here is your design functions, design variables, 1, 2, 3, 4, and then drag and leave our objective. So we wanted to minimize this and maximize this. And all these values represent an optimal value. And already by exploring this one, you will see something interesting here. So see that we're in line with the previous cases, the single objective that was something about 0.54, 0.55. So see that we have all these values. And it slowly is increasing because you're making that effort larger, but you keep low, but you're increasing lift. So in this case, would be better if you look at LD ratio, the ratio of lift drag would be better to have one of these cases still with low drag, but then you will see that suddenly you have this jump to another solution here. So still this is low drag, but you're producing more lift. So in all those function evaluations that the Mulga conducted, these are also non-dominating. It's called non-dominated solution. It cannot get any better than this. So you will have all these possible solutions, and at this point it will be up to you to pick up which one you would like to use. You don't have a single one, you have multiple solutions. So let's do some plotting about this to show you the Pareto in this case. So one thing that, well, I run the case is you don't want to run this exact output. You have it here. Okay, I already put it there, so you can get, you can plot everything from that. So let me come here. So I have this small, these are the steps to do the plotting with new plot. So I will go with new plot. And basically I will plot final solution. That is my Pareto front. So let me go and take this part here and paste, and there you go. This is my Pareto. It's a little bit small. Let me increase. Let me see. Go here. Okay, so well, let me make this maximize here. Okay, and there you go. So this is with Pareto. So this area here is the area where we have a small airfoil, you make it larger, and then see that you have this jump here. So this is a discontinuous Pareto. You go here, discontinuity, then some solutions here, and you go to this solution. All these solutions are optimal. So here, well, easily you can say, okay, I don't care about these solutions. These are no, probably it's a very big airfoil. I don't know, but maybe you want a big airfoil in the sense with a lot of thickness because it will have more inertia. So we talk now about multidisciplinary. So you know that have more inertia from the structural point of view, it will weight less. So since that you should be aware, you should always cross-relate your data. But let's focus in this cases. So all these cases represent an optimal one, and then you have all the data there. You can see the geometry. So let's look at the minimum and one here, and probably one of these large cases, how that geometry looks like. So our Pareto, and just to plot also more information before now doing that paraview stuff. So look at that. We're going to plot population 1, 5, 10, 15, 20 all together. So let me go here, plot, and this is what we have. You have all these populations. So the colors that you see there, let me hide a few stuff there, is how things are evolving. Okay, so see that it start, okay, let me, okay, it's not hide away in any case. It start from initial population and see that very slowly is moving towards this Pareto. And no, I don't like what I have there. Let me go and plot it again. So, okay, now it's better. Bah. Ah, let me get out there just to show you this. Always is usually my display screen that, let me scale it to proper dimensions, and this should work now. Okay, so bam, 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 bam. We go here, here, and this one. Okay, so now it's much better, and I think it's okay. So now it works. You have the problem, the same problem. Well, just scale your screen. Any case, see that initial population or population one is not the initial one, and see that initially it will deploy all these function evaluation experiments and start to measure now where it will get the improved, what are the better solutions, in what direction should I move. So this is your Pareto here, and then it goes to population 5, and see that now already start to evolve toward these solutions very slowly. Population 10, then population 15, and at this point population 15 you start to see that it is identifying those values, and population 20 you have there, and there are more. Let me see how many populations do I have here. So 40 populations you want, so it's keep evolving, but already at 10 you start to see some trend there. So maybe some start running a big case, whatever. You look at these populations and you start to see that everything start to cluster in an area. It might be the case that you can stop your simulation here and do something manually just to speed up things, but it's I recommend you just leave it running to get your complete Pareto, but it's up to you. So this is it, and then for instance, let me also plot here as well. Let me add the discards solutions. So I think here discards. Let me copy this and add it here. And discard all the cases that was discarded during the evaluation, or I think the last evaluation that was discarded. Okay, it's not accumulating, so you can see how things are discarded. And also you have table out, and table out you will have here you have everything that was evaluated. Okay, so be careful that table out is not your optimal solution. Your optimal solution, you have identified final data. So see that table out, all the cases that were evaluated, you have it here. So interesting that in some cases might happen that you can violate some constraints, so there will be some points here. So let's just to go back. I think I have it in this slide. So see that in this case, you have initial iteration. Look at that, you have also solutions here. So the Pareto, in this case, you had solutions that were uh, beyond this, let's say, threshold, and then after iteration one, they are discarded because they are violating a condition. In this case, that didn't happen, but can happen, so didn't happen, and yeah, there you go. Well, now let me close. So this is how you evaluate the data in this case. So remember, these are all your populations, so you can see how things are evolving. Final data, you have all the points that you can use to construct your Pareto. And now let's see, for instance, the Pareto, and let's say, for instance, this case. Let's see, okay, that information I need to cross-relate to see the specific work directory. I need to cross-relate it. Somewhere in your string, in your output string, there should be, you should see that information. I don't recall where, but in any case, it's not a bit of a deal. So let me go there, and you have one key, so it will be 1631. So just to show you that there are different solutions, so cd word there 16, I forgot, 31. Then let me launch Python, apply, and okay, so I still go here. It's not much. Okay, let me go and adjust again this display settings. Sometimes can be a little bit annoying. And yeah, I have it there. Bam, 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 bam. Let me launch again. Okay, so now it's fine. So you see that the classical solution, we are familiar with this one. So this is that exactly, or very close to what we have in the other methods. So this will be the minimum surface area. And then let's check another solution in my Pareto. So in my Pareto, we go here and let's go to the other extreme here. And to show you that in all those directors, we have different solutions. So let me check this one. That will be another extreme. And this one will be 15, 1451. So 1451. And let me go Pataphone. And there you go. You have your other airflow and so on. So in this way, you can check each one. So you want to plot all the solutions, get the shape while you write on a small script. But I'm a little bit curious about this solution. Let's see what are those solutions. So this is that discontinuity. So let me go to this one. I already see that this one, okay, this variable. So I think it will be the thickness. It will be a little bit high. So let's see what we have in this case. I'm curious what we're exploring. 1937. Okay, so see that clearly, and this is very important. It's not only looking at the data. So as you look at just your objective functions here, probably you have no idea. Well, if you know your problem, when you check these numbers, you will know that it's not something that is okay. But when you plot that one, see that clearly this is not something that you will like, as an airfoil. So thinking here that you want to create from that shape and get something airfoil-like, slender, aerodynamic. This is not nice, but yeah, it's one of the possible solutions. So not necessarily everything will get that shape, or not necessarily. Let me rephrase that. With this problem formulation, we can get solutions like this that maybe we might not interest in. So what we can do is add a linear constraint to avoid some situations, or maybe add a non-linear constraint. So adding a linear constraint is quite easy. So remember that those linear constraints are here, so you can add also inequalities and so on. So for inequalities, go in documentation, and I haven't done anything about that. I usually don't put inequalities in linear inequalities, but it's this. So you put your matrix and you say no, your inequalities and so on. So usually I don't do this. I just put the normal values, but I add inequalities when it comes to non-linear constraints, since that needs to be computed. So for instance, you have these quantities and you would like to compute, let's say, the area or the distance between points. So that is an extra computation that you need to put here. So now that we have explored this, and hopefully you get an idea how things work. And by the way, to show you also here, I think I have a figure, and here image. So here you have the possible solution, 4 possible solutions that I plot. So see that this is in the nice part of that Pareto. So from the minimum one to the maximum one and 2 in between. So all those are nice. Probably I will lean towards this one now because it will give me the best LD, but it's up to you. So now let's change a little bit the same case. I will run it live just to show you also that nothing is crashing, and the importance, and stress this, the importance of having a fault tolerant loop and be sure that everything is working. So remember to clean out everything before running. And the small modification that I'm going to do is to add a nonlinear constraint. So something that we haven't done yet, and we're going to do it here. So bam, 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 bam. So to add that is simple. You go into Dakota case, and the nonlinear constraints are objective functions, quantity of interest. So what you need to do is this keyword, nonlinear inequality. There are different ways. You have nonlinear inequalities and equalities. In this case, I want an inequality because I want that matrix, that I want that quantity that it will be. I will say that from those values, recall that I have for leaf, I will say I want to constrain leaf, and just to make it clear, and let me bring back that I have the solution here and final data. So look at leaf. So I have negative value. I want to avoid negative leaf. Okay, but also by looking at this one, also I want to avoid leaf values in 0.25 because it's going to generate these strange cases. So I can limit to 0.23. Okay, so that's what I'm going to do. So here you just create it nonlinear inequality. You have one constraint. You can add as many as you like. And remember again, I broken record when it comes to this, but it's very important. Documentation. You go there, and if you want to know a little bit what is happening, you have there the explanation. It's very good. I like to do it because also the Dakota documentation is quite good. Upper lower bound. So here I'm guaranteeing that everything will be positive, and I will go up to 0.25, even though that it should be 0.23, but just to see what happens. Okay, but it's up to you. And now let's run this case. So this is the the modification that we need to do, and to stress that this quantity needs to be computed. So for me, it will be leave again. So if I go to simulator script, I need also to have that information available. So if we look at the script, so look at that, this I'm constructing here. Now this is my output filter, and let me go back to that concept output filter, which goes is very important, this output filter to keep Dakota running. So this is what we're doing, filtering that data to convert it into the format that Dakota likes. So I just need to add that new information. So in this case will be this line here. I will erase the comment, which is repeating this information, but here can be anything. So for instance, would be very interesting, and I invite you as an exercise to do it. So because this data that you have, let me open this one. You are computing and computing. You have the same variable, but you have lift, drag, and moment. So that variable, new variable, not necessarily needs to be lift. Again, that I'm repeating. You can say here moment, and you can do your optimization to have the moment a low value or a positive value, or you can make it equal to something. So many times that happens. So you can add that, or probably you can compute the surface of that geometry to minimize also the surface. So those are quantities that are derived, that are not directly the same variables, okay, and needs to be computed, no linear constraint. So have that in mind. So just erase this comment, and we're ready to go. So exactly the same will happen, but with that new constraint. So let's run the case, and I will let it run again live just to show you. And always I recommend you to save the trace, the standard output input, the standard output, and also the error output that you have it there. So let me hit there, and off you go. So nothing, everything is okay, didn't complain, fault tolerant. I double check everything, and at this point, let's wait. So it will be probably will be faster than the previous one. I don't know, but in any case, I will leave it running and see you in a while. Okay, I'm back. So, well, again, we have a boatload of simulations, function evaluation. So let's look at the data tree. So in this case, I think was a little bit faster. Okay, still 2000, but remember that now we have that. Let's check the final data file. Okay, And now in final data, remember that we added that nonlinear constraint. So if I open this file here, and what we did simply say that I want positive value up to a maximum of this to avoid those strange solutions, and see that now by enforcing that, so design variables 1, 2, 3, 4, drag and leave, and the second one will be for the linear nonlinear constraint, and see that now we don't have, like in the previous case, uh, the negative leaf. And now if we check here, we go up to 0.25 and still we get those strange solutions. So I just did it on purpose because well, I knew there's a put 0.23, you avoid that. But just to show you that you can control things. And this is just built in this argument that remember that you need to formulate your problem, and sometimes you over constrain your problem and you can converge to what you think it is the ideal solution. So for instance here, if I start to add more nonlinear constraints, probably I will just limit to this one, which I think are the optimal solution. So probably a single one, but you are missing out a lot of stuff. So usually it's no iterative process, you mix different techniques and so on, just to get a better understanding of your design space. Yes, it is expensive, but in general, optimizations is very subjective. Also, this is interesting when we look at this Pareto, because it is the big question: that can optimization method give you a global optimal value, the best value overall? No, there is no guarantee, because you always will get a small improvement that you can clearly see here in the Pareto. But if you do single optimization also, you arrive to something that you might think is a global, but then you move a little bit in one direction and you will optimize. So basically you will run your optimization now until you run out of time, which is the most precious commodity, until you run out of money. You are just putting everything now into your cluster or whatever, or until you get tired. That's all. But optimization data can be an infinite process. So yeah, try to avoid perfection in optimization, because perfection will make things very time consuming, but also they will make it in very expensive. No, perfection tends to be, the enemy of profitability. So you will waste money in computer and so on, and your own time. But anyways, I digress a little bit. So yeah, we have a nice solution, push, very elegant. And same stuff, you can explore what you have here, look at your solutions, and this is how we conduct this multi-objective optimization. I want to stress something, that initially when I launched this case, and I let it run, like, I don't know, for an hour, and then when I check, I didn't get the right result because I make a mistake in the simulator script. So be very careful to save everything and make it. I think I erased this comment and then I didn't save the file, so I had to press Control S or save it. So see that those small details, they do count. So always check that everything has been saved, your files are in order, so you don't waste any time. So your final data, and then well, you can check everything, and there you go. Now we have a better case here. So at this point, I think pretty much we're done. Something interesting that probably when you see this, play back this one, uh, you saw that I was doing the post processing while everything was running. So you have this running, and you don't need to wait to the end. You can open Paraphone, you can do your scripting, everything. And if at one point you feel that you have arrived to that optimal solution, just stop the process now. And it's kill the process now. So just can be h-stop, just identify the process, or Control C if you have that terminal window. That's all. Okay, so at this point, this case is multi-objective. Hopefully you have an idea what is happening. And I just want to comment something, because you have another case here. I'm not going to run it here, or I already have the solution. But what I did here is multi-objective. Now the SO stands for single objective. What does it mean that? Because it can be a little bit confusing. So basically what I'm doing here, I have two objective function, minimize, but it's the same objective function, which is drag now. So just to show you that the MOGA should also converge to the same solution of the SOGA if you put the same solution that you see here, drag one, drag two. So I'm repeating that just to show you a different method. Okay, so let's say that I feel like I have enough time today and play with these cases. And here you have the solution. And if I open final data, remember final data, you have that Pareto. But as we have the same functions, I put it here, a single solution, which will be equivalent to a SOGA. Probably here also I change here also I play with the population size, maximum number of iterations. So it's not convergent to the precise exact value that we know is something about 0.5, 0.5, 0.25, and 0, no, minus now. But it is in that ballpark, in that area that maybe if I go to the previous one, oops, here, and oof, final data. So see that maybe it will be this solution that you get here, 0.588, will be something around here. Okay, one of those probably, yeah, it's a little bit different. I have something different, 0.63, that this one is not exploring that. But look at that. Well, you get different solutions, different method, but the idea, I hope, is clear the concept. So this is it. Okay, multi-objective, unique to the new objective functions. Then also is the one you can add nonlinear constraints. Remember, these nonlinear constraints, another quantity that you compute. So in this case, now we have three quantity of interest. So when you post-process this data in your results out, you will have 1, 2, 3. Okay. In the previous case, it was just 2 as you put here. So be careful about that. Set up everything, the sense of the functions, you put it there. By the way, you can have more than 2 there. So usually it's 2, but you can put 3, and then you can say the other would be, I don't know, max also. So yeah, you can do it. Honestly, I haven't encountered a problem where you can do that. So usually you split the problems and to avoid, because that would be even more expensive if you put 3 there. So this is it for this case. Very interesting. So at this point we have covered a lot, I have to say, a lot. So the next thing that we're going to do next video, so we have covered derivative free method, design space exploration, grading methods, multi-objective. Then we move to the SBO, which is surrogate based optimization. We're going to see 3 techniques. The one I like, I already talked about this one, the EGO, efficient global optimization, but also we have global and local optimization at the surrogate level. So you will see the difference is a slight different, and kind of you have to be aware of some issues here, but that's all. And finally, I'm going to introduce XGBoost, which is a machine learning tool, a fantastic tool, unbeatable. So basically, XGBoost is to construct meta models. So we're going to get the data from the DAS or whatever, and we construct a meta model. So it will be equivalent to using one of the models that we use in SBO, which is a Kriging model. So just to show you that that's all, but it's nothing fancy. And that's all. Well, thank you for your attention. See you in the next video. Bye.